Hello everybody and welcome to the NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective. And this is lecture number 27, and the lecture topic is Introduction to Semiconductor Heterostructure, part 3 of that, where we were studying the basic concepts of heterostructure. So, we will start from where we have left in our previous turn, and that is basically your image force barrier lowering, right. So, let me explain to you what do I mean by that. We have already, but I will recapitulate what we did. So, this is known as IFBL, image force barrier lowering. Let us suppose this is semiconductor and I have this electron here. It effectively means that I can place, in order to have its image charge particle, which is a positive charge, I need to place a charge particle of positive nature in the same distance as it is from the interface between metal and semiconductor. So, if I place a charge x here, it also plays mirror charge or a symmetric charge onto the metal side. And how do I model it? I model it in such a manner that the distance from the interface of the metal semiconductor to the charge on both sides are exactly equal. So, if we apply the Coulomb's law, what we will see is that the force applied between the two of them will be minus q square by 16 pi epsilon naught x square, where x is the distance between them. This is the force which is between the two particles is there, right. This basically is known as the image force, which I was referring to in the previous lecture as well as this lecture. This is known as the image force. Now, what does it do is, therefore, that it tends to make, so every time you have a negative charge on the semiconductor side, let us suppose, in a sense you are inducing a positive charge on the metal side, right, because of which the barrier height is actually going on reducing on the semiconductor side. Because if you understand, more and more negative charges on the semiconductor side and more positive charges on the metal side will make the barrier go low and low onto the metal side, right. And therefore, if you plot the barrier height, it will be something like this, it will go like this. More is the charge carrier, more it will go down on the negative side, right. So, what happens in this case is that what we have learned from this is that there will be a basically a IFBL or an image force barrier phenomena taking place. Now, this statement which is shown here, it writes that the Schottky effect is the image force induced barrier lowering of the potential energy for the charge carrier's emission when electric field is applied. Now, if you apply now an electric field, there will be an energy there which will be given as Q into E, where E is the electric field which is available to you, or Q into V will be the energy which will be available to you. If you look at the electric field, it is nothing but dV times dV dx, and therefore, if the value of V is there, there will be an effective energy barrier lowering because it will be a negative charge, because of which the barrier lowering will take place. So, let us look at this energy band diagram between the metal and the vacuum, let us suppose. This is all phenomena is towards the metal side. So, if you look at the metal side, you can see that Q phi m is my basically the work function of the metal, right, and this is my barrier height Q phi b. Ideally, what has happened is that if everything would have been correct, which was the ordinary case without any barrier lowering, then my phi fm will be approximately equals to phi b in this case, right, because the energy barrier and the barrier height which you see here phi b will be very close to each other. However, because of this image force barrier lowering, the energy at this metal side is actually, or the metal side is actually lowered by a factor of q delta phi. So, this will be q times delta phi which is happening, this lowering takes place. So, ideally, so if you assume that the electric field is a linear field, then I would assume that this is the linear value of the electric field which you will see. This is x and this is the energy, and therefore, this is the line which goes linearly with respect to x. Now, if you take the image potential barrier energy, it comes like this dotted curve which you see here, right. It is very high at near the interface, but as you move away from the interface, as obviously the energy will go on lowering and becoming very much close to 0, and it almost becomes asymptotic at higher values of x. What it tries to do is two things happens. At lower values, which is very near to the interface somewhere here, you end up having this dominating, and therefore, if you look at this curve here, this curve is actually following the dotted curve, this curve. very near to the interface, which is much below xm value. But above xm value, what is happening is it tries to follow this curve, which is the electric field actually available or energy field actually available without image force barrier in lowering, and it becomes significant beyond the value of xm. Below the value of xm, the image potential energy is much large. Above it, the value of this is very large, and therefore, as you can see, it first increases and then lowers down drastically and asymptotically with respect to QEX here between the metal and the vacuum, which means that if you have implication of this is that when you have this such type of effects, you tend to reduce the dimension of the energy barrier, right, and you have much heavier, a larger number of electrons or charge carriers being permitted from metal to semiconductor and vice versa. Let me come to the Schottky contact now, and let me come to ohmic contact. We have already discussed this point, but we will go one by one. Ohmic contacts are basically metal on a heavily doped silicon. So, if you have a metal as well as an heavily doped silicon, then this is basically an ohmic contact, right. And if you do on a lightly doped silicon, then this is basically a Schottky contact, and this is rectifying contact. Rectifying contact primarily means that the resistance is very low on one side and is very large on the other side. So, as an example, if you look at this PN junction diode, for example, this is sort of a area in which we can say that, you see, in the forward direction the resistance is very low, relatively low, and on the reverse side the resistance applied is very high. So, it's basically sort of a rectifying contact, whereas if you take an ohmic contact, the resistance is low across the path both in the forward as well as in the reverse direction. So, what we have done is that when you have a Schottky contact, it will be rectifying in nature. When you have ohmic contacts, it will be low resistance. Typically, ohmic contacts are between metal and heavily doped silicon, and Schottky contacts are between metal and lightly doped silicon. Let me take up an example of a Schottky junction using energy band diagram, right. Now, look at the right hand side, this figure. This is basically my isolated metal. So, this is isolated, which means that I have still not joined the metal and an n-type semiconductor. They are separate, and then on the left hand side, this figure, we have not applied the bias, but they are separated out. So, if you look at this right hand side figure here, you will see that this side is metal, this side is metal, and this side is semiconductor, and this side is metal. So, obviously, the distance or the energy between the conduction band or the Fermi level of the metal side and the vacuum level is q phi m, the work function, and as you can see, the conduction band and the Fermi level are coincident at this particular point. Onto the n type, since it is n type, Fermi level is closer to conduction band, q chi is the electron affinity and q phi s is the semiconductor work function. So, in this case, phi m is greater than phi s in a sense, right, and as you can see, the metal work function is much larger as compared to the semiconductor work function. So, that is the reason that conduction band of the semiconductor is on a much higher level as compared to that of the metal. Now, this gives me an idea that obviously this is an n type. Now, what I will do is I will take these together, both of them together, and then we try to merge the two together, which means that join the two together. When you will join, there will be a thermal equilibrium take place and the Fermi level will align, and that is what I have shown here, that the Fermi level is aligning both sides, Fermi level is aligning. And since you have joined it, the number of electrons on the n side have actually become reduced. You can see that the energy band diagram near the interface have actually gone up, right. It is almost like giving positive bias on the n side, right. Without giving a bias, you can understand this particular point, that if you give a bias, the whole band will shift to the bottom because it is minus q times v. As it shifts to the bottom, near the edge, it still remains at the top. Why? Because the reason it is that by that time the effect of potential is actually being lost near the interface. So, when you apply that, this goes at the top, and what happens is that this is the electron affinity which you get for this is the vacuum level, right. The work function difference, this is the electron affinity, and this is the built in voltage which I was talking about in the previous turn, QV built in, right, and this is the work function difference. Now, the effective value of q phi Bn is equals to q phi m minus chi, right, which I have written here also in a same manner, which means that the Schottky barrier height is actually equals to the energy difference between the Fermi level on the metal side, the work function, and the electron affinity. The difference between them is this one is basically my barrier height. Why? Because this much amount of energy barrier, the electron on the metal side have to rise in order to go towards the semiconductor side, right. So, this is my barrier. So, let me remove this, let me erase, and then let me see what happens here. So, if you look at this interface here, this is the barrier height between this, because there will be large number of electrons near the Fermi level in the conduction band, and you require an energy equals to q times phi m minus chi, which will make it go to the top, right. So, one way to reduce this barrier is try to make your phi m as large as possible, right, and therefore, that will be closer to chi. So, phi m minus chi will be smaller, and you will have a lower sort of a Schottky barrier height or a Schottky barrier potential. So, this is basically referred to as the Schottky barrier height or Schottky barrier potential. So, this is the basic formulation of a Schottky junction with isolated on the right hand side, on the left hand side it is basically non isolated. If you look very carefully, then if you go back to the previous graph, then EC, so it is basically EC minus EF. You see, what is the value of built in potential is nothing but Q phi Bn, the barrier potential, minus EC minus EF. What is EC minus EF? EC minus EF is what? EC is this one, EC minus. So, this, right, plus this will give you this, right. That is what is written in this next statement here. So, phi Bn minus ECN minus EF will give you Q phi B. So, if I do EC minus EF, it comes out to be KT ln of NC by ND, right. NC by ND is conduction charge and the donors which are available to us, and this gives you the value of V built in or Q times phi built in. So, once you attach a N type semiconductor with metal, you tend to therefore have some depletion region available to you, because these surface, because of the surface charge, there will be some electrons which will be leaving the metal and go towards the semiconductor, or from even from the semiconductor it will try to go towards the metal. As it starts to go towards the metal because of some phenomena, there will be donor atoms which will be available, which will give rise to a depletion thickness, and this depletion thickness will depend upon built in potential and your applied potential. So, if your applied potential is more and more positive onto the N side, the energy band diagram on the N side will actually go down drastically, right. As a result, your W depletion will become much higher, and if it is forward bias, it will get lower. And one point to be noted here is that W depletion is inversely proportional to 1 by root of ND, which means that if higher is the doping concentration, lower is the depletion width, right. And therefore, in many of the whenever you do a very let us suppose you do an ohmic contact. In ohmic contact, you are anyway doing it with very high doping concentration. So, for example, a metal and a P type or a metal and an N type, then the ND value is relatively very high, which implies that the depletion thickness on the semiconductor side. So, this W depletion is the width of the depletion only on the semiconductor side, right. So, on the semiconductor side will be as low as possible, because your ND value has actually increased to a large value, and therefore, your WD or W depletion will be as small as possible. So, if you want to make your depletion width small, one way to do it is either reduce your V built in, but that is not possible because the type of metal which you choose is already predefined. Therefore, one thing is that try to make your doping concentration high, and in the semiconductor side to make your depletion width smaller, though that has also got some adverse effect onto the device characteristics. Let me come to the ohmic contact now, and it is basically, as I told to you, and it allows you to current flow from metal to semiconductor and vice versa very easily. If you look at this diagram, N plus semiconductor junction. So, I am showing you the energy level diagram for a metal semiconductor contact, right. So, it is metal N plus semiconductor contact, highly doped, and I have not given any bias, and therefore, you see your Fermi level on both sides, the red colored dotted one is constant, right. And since it is constant, I can say its thermal equilibrium has been reached. However, when you do an N plus type semiconductor and you try to merge with the metal atom, what happens is that there will be a dip in the conduction band edge and the valence band edge. There will be a fall energy will fall down, which means that on the periphery of the interface nothing happens, but near the edge it falls down. The reason being that the metal and N plus is basically having large concentration of electron, right. So, what will happen in this case is that they will donate one electron will go to the metal side, and there will be a depletion region formed near the metal semiconductor interface somewhere here. There will be a depletion width here available with you, right. And this depletion width will be depending upon how much N type your doping concentration is. If your N plus is having a high doping concentration, you will see that this will, rather than standing here, it will actually bend from this particular point. The bending will start from this particular point, right. And as a result, what will happen, your depletion width thickness will actually reduce at particular point. So, one way to detect where is the ending of your depletion width, I have also discussed in the previous turn, is to check where your energy with respect to x goes to 0. That is the point where you should actually look into the point as the edge of the depletion, right, because that is the electric field will be having 0 values at that particular point. So, this is an ohmic contact which I showed to you. Ohmic contact, why? Because electrons can easily jump. So, you see your band, your q times phi m value is relatively very small. So, metal electrons can jump and go to the semiconductor, and in semiconductor, since already your conduction band edge is larger than the Fermi level, there will be electrons can easily flow from this side to this side. So, when electron flows from this side to this side, the J value or the charge carrier density will be from this side to this side, it will move from this side. So, this is J semiconductor to metal, and if you look at J metal to semiconductor, it is in this direction, right, because the conventional current is in the opposite direction to that of the electronic current, and that is the reason you will have both sides a well defined electronic current. Now, let me explain to you maybe the material composition. So, let me look at the semiconductor junction. There are two types of semiconductor junction. One is known as a homojunction, where the material is same on both sides of the junction, and we have a heterojunction where the material is different on both sides of the junction, right. Similarly, if you look from the point of view of band gap, then we define homojunction to be a uniform band gap, whereas heterojunction to be have different band gaps. So, that is a major difference between a homojunction and heterojunction, is that homojunction gives you uniform band gap between one point and another, whereas heterojunction gives you different band gap. For example, if I take a simple PN junction diode, right, silicon based PN junction, that is a homojunction. Why? Because both sides of the metallurgical junction you have only silicon, and silicon is always a fixed value of Eg or depletion width, and therefore that is a uniform band gap. Whereas, if you take, say for example, gallium arsenide or indium gallium arsenide and then try to sandwich them together, since the band gaps are different, there will be discontinuity somewhere, and they will be referred to as a heterostructure or heterojunction with different band gaps, and there will be discontinuity in the energy band diagram. So, we can distinguish therefore the semiconductor junction from two point of view. One is the material composition and another is the band gap composition. Now, let me come to the heterojunction and explain to you about the heterojunction. So, if I take a heterojunction, so it is something like this. So, I will explain to you, maybe I will do it like this. Let us suppose I have this and this. So, when you try to mix them, when you try to bring them, so this is a lower band gap and this is a higher band gap material. When you try to bring them closer, there will be always a discontinuity at these particular points, right. There will be discontinuity at the point where there will be merger of the two, and therefore, as I told to you that the energy band will have a discontinuity at the junction interface. At the junction interface, it will have a discontinuity, and it may have a abrupt junction in which the semiconductor suddenly changes from a narrow band gap to a wide gamma material. What do I mean? Abrupt is something like this, where the doping concentration suddenly falls down at the junction. This is an abrupt junction, where the doping concentration suddenly falls down to a value which is very, very low, right, from a very high value, right. Now, the idea of a heterojunction to be successful, it is also important that the lattice constants of the two material must be well matched. Of the two materials mean the two materials on the other side of the gap. So, if I have this metallurgical junction here, then this is material 1 and material 2, then material 1 and material 2 should have a well defined matching of lattice constants. That is very important, right. If it is not so, if there is a lattice mismatch across the two, there will be a problem of stability as well as stability of the semiconductor heterostructure itself. Now, as I discussed with you, there will be dislocations also available. That is what I was talking about. There will be instability as such. So, if there is a lattice mismatch between the two, then what will happen is that you will insert large amount of interface states between the metallurgical junction, and these are acting as distortions to the actual since. Since this is a distortion, what will happen is that it will degrade the junction characteristics. Now, let us take up a gallium and gallium arsenide metallurgical junction. There you will see that the mismatch is hardly 0.13%. You see, the mismatch is so small, and therefore, a very good heterostructure system is basically germanium gallium arsenide, right. Germanium gallium arsenide is a very good heterostructure, as their lattice constants are very close to each other. Similarly, if you take a gas AlGas, which is this one, gallium arsenide and aluminum gallium arsenide system, then the difference is approximately equals to 0.14%, right. The difference is just 0.14%. So, the lattice constant differences between the two edges is so small that you will never find an interface states coming into picture. Moreover, interface states also have a problem, and the problem is that these are temperature dependent states. So, when the temperature varies, the location of these states as well as the values of these states will also vary. Once that happens, then the threshold voltage will change, the off state current will change, and so on and so forth. So, that is a major problem which will happen if the lattice constants are not matched properly across the network. So, with this, let me give you a recapitulative, but before I recapitulate, maybe one small thing which was left in the previous discussion was that this is an ohmic contact, right. So, I will like you to do an exercise where you do a metal P plus type semiconductor band diagram. All of you, please, if when you are going through this lecture series, then since you have understood about metal and N plus type semiconductor, please draw a band diagram for a metal P plus semiconductor, right. For a metal P plus semiconductor, when you do, just keep in mind this Fermi level be shifted towards the valence band, and also remember, when you draw a band diagram, for all practical purposes, keep the Fermi level same. If you do not apply any bias, then under thermal equilibrium, your EF should be constant across metal semiconductor contact. Keep these two in mind and then draw the line, and then you can easily formulate the ohmic contact with either N plus layer or with P plus layer. Please understand, at this stage we are not discussing with you anything which is N plus plus or P plus plus semiconductor. N plus plus will, even if this is a degenerate semiconductor, then this Fermi level will actually be very close to the conduction band. In fact, it will go inside the conduction band to a larger extent, almost like a metal. Then also you need to find out what will be the band diagram. The conceptually the same structure remains, but the band diagram will change, right. So, with this we have finished the understanding of this lecture. So, let me now come to the recapitulate you what we did in this lecture. Now, we did initially, we looked into what is known as a Schottky, and then we went for ohmic and non-ohmic. Obviously, this is ohmic contact and this is non-ohmic contact, referred to as rectifying contact, and we also refer to this as a non-rectifying contact, right. So, we have two types of contacts, and we understood using rectifying and non-rectifying. I will do it in the next turn again, how to draw its band diagram, right, for say a metal and N plus semiconductor. You are also told to draw a metal P plus semiconductor, and we see that this ohmic contact will give you both electron flow in one direction and both the directions. And then finally, we looked into heterostructure and we saw what is the meaning of heterostructure. I will deal that in much more detailed manner in the next lecture, and how lattice mismatch is important for the functionality of heterostructure, that we also saw. With this, we finish this lecture, and we'll meet next lecture with heterojunctions. Thank you.